All right, in this worked example, we're looking at first, state the principle of conservation of momentum. Different ways to sort of state this correctly. But one way is to say, in a closed system. And what does that mean? That means there is no resultant force acting on it. There's no outside force. So in a closed system, total momentum in any direction is constant. So that note was on the board the other day, although we might have talked about what a closed system was. It's good to sort of put that in words. So in a closed system, one where there's no resultant force, the total momentum in any direction is constant. An equal way of wording that is to say the total momentum of all the objects before a collision equals the total momentum of all the objects after the collision, right? So that the momentum is conserved before and after collision. If you said something to that effect, 2 marks for that one. The question goes on to ask us to calculate the total initial momentum of the 2 balls. And so you can kind of see maybe still at the top there that those were the sort of initial conditions there that give us both the mass and the velocity for each of the particles. And they are traveling in the same direction. And so we don't have to sort of like subtract one velocity is not negative relative to the other one. So mass 1 times initial velocity 1. Well, those objects are actually called x and y. So to be consistent, so mass of x times initial velocity of x plus mass of y plus initial velocity of y, and that should solve it. You do have to convert into kilograms because the units of momentum they want are Newton seconds. So remember that a Newton is a kilogram meter per second squared. So they require us to convert our mass into kilograms. So 0.4 kilograms times 0.65 meters per second will give us the momentum of object X initially, and then 0.6 kilograms times 0.45 meters per second give us the initial momentum of object Y. Remember that force is the rate of change of momentum. And if we multiplied both sides of this by delta t, we get force times time equals change in momentum. This is called impulse. Impulse equals the change in momentum. And it's a clear way to sort of see the units, Newton seconds, Newtons of force, seconds of time, are the same thing as the units of momentum, where it's mass, kilograms times velocity, meters per second. Substituting in kilogram meters per second squared for newtons will cancel out one of those seconds and it will agree, on the side. So a Newton second of impulse is the same thing as a kilogram meter per second of momentum. Impulse equals the change in momentum, impulse momentum theorem. Going back over to our calculation there, 0.4 times 0.65 is 0.26 Newton seconds. Right, same thing as a kilogram meter per second. 0.6 times 0.45 is 0.27. 0.27 Newton seconds plus 0.26 Newton seconds gives us 0.53 Newton seconds. If you correctly calculated that, well done. And if you got like 530 or something like that, you probably didn't convert into kilograms. And so just give yourself the feedback of, oh, got to convert to kilograms. We've seen where sometimes we don't need to, like if we're just solving for velocity, the units of mass are going to cancel as long as they're all the same. But when it's a question like this and it wants Newton seconds of momentum, then we're required to convert grams into kilograms. So keep that in mind. The fact that they're going in the same direction is all that's important here. So we add them. Like one velocity isn't negative relative to the other one. And so indeed we sum the two momentum. There's total momentum in the right direction. So one doesn't oppose the other one. So it's just the sum. The question goes on to ask us to calculate the velocity v. And so after the collision, we're sort of looking at the situation up there. What is this velocity v over here? Keep in mind, there's 0.53 units of momentum initially. Right, like the answer that we just got here was 0.53. And so if we say, well, the initial momentum has to equal the final momentum, and I've already calculated the initial momentum to be this many Newton seconds, the final momentum is just mass x, final velocity x, which is given here, plus mass y, v, right? What they're just calling v. And you can say v, y, but I'll just be consistent with this. All right, and then we can substitute in 0.4 kilograms, 0.41 meters per second, plus 0.6 kilograms v, equal to 0.53 seconds. We can calculate that object x has a momentum of 0.4 kilograms times 0.41 meters per second, or 0.164. I'll just say Newton seconds of momentum from that, plus 0.6 v equals 0.53 on this side. I'm going to rewrite it over here. 0.53 equals 0.164 plus 0.6 v. I dropped all the units because I know that everything's going to cancel out to give me the correct units of velocity. You know, all my units sort of agree here. I convert into kilograms. So subtracting 0.164 from both sides, get 0.366 equals 0.6 v, and then last step, divide each side by 0.6. And we calculate that velocity as 0.61 meters per second. Finally.
Everything that I have, if they're going in the same direction as I, I mean, if they're going like against each other's and if they're going in the same direction.
So we'll get to that. So I think if you're calculating the relative speed, then if they're going in the same direction, you subtract. Say it again. So when we calculate relative speed, and we're coming up to that, so I think the question paper goes on to ask us, what's the total initial kinetic energy of the two balls? But then this idea right here, we'll sort of get back to that. And so it's good to just sort of see, you know, okay, well, if we subtract it instead of, you know, adding that, sort of why was that, you know, sort of incorrect here? And what note did you have in mind and say, okay, I just incorrectly applied sort of this idea. Kinetic energy is 1/2 mv squared and wants initial kinetic energy. And so here we just have to sort of just trust our definitions here. 1/2 mass of x, initial velocity x squared, plus 1/2 mass y, initial velocity y squared. And we're just summing the initial kinetic energies of those objects to get the total initial kinetic energy. So it was 1/2 0.4 times, I forget what it was. The initial velocities were 0.65 and 0.45. .65 squared plus 1/2 0.6 0.45 squared. So those are the numbers that were given. You do still have to convert grams into kilograms because a joule also has kilograms sort of embedded within that derived unit. And the derived unit joule, like a joule is a Newton meter, right? We already know that a Newton is a kilogram meter per second squared. So you do have to convert those also. All right, so we've got 0.65 squared times 0.4 times 0.5. And so there's initial kinetic energy from object X equal to 0.0845 joules. From object Y, we have 0.45 squared times 0.6 times 0.5 equal to 0.06075 joules, for a total initial kinetic energy of 0.14525 joules, or 0.15 joules rounded. Explain how you would check whether the collision is elastic. So on the chalkboard it says, why are most collisions inelastic? Because usually kinetic energy is converted into other forms when things crash into each other. There's sound, there's heat, there's deformation of material. In order to check whether a collision is elastic, we could say, well, since we just calculated the initial kinetic energy, Why not calculate the final energy, kinetic, and compare it to that initial? Because if the collision is perfectly elastic, then the final kinetic energy will equal the initial kinetic energy. The other day, we derived an idea that says, oh, because that's true for a perfectly elastic collision, then the relative speed of approach will equal the relative speed of separation. If the collision is perfectly elastic, then how fast the objects see each other initially will equal how fast they see each other after the collision. And so that's where, if they're moving in the same direction, we subtract. To calculate relative speed, if things move in the same direction, we subtract. If they move in the opposite direction, we add. For this problem, everything is moving in the same direction. So remember that the velocity we calculate here is 0.61. The relative speed of approach before the collision is the difference between this velocity and this velocity, because same, you can subtract. So 0.65 minus 0.45 equals 0.2 meters per second. That's where we subtract to calculate relative speed. Same, subtract for relative speed and for relative speed only. If we're calculating momentum, that's where we look at, well, one vector might oppose the other one. One might be negative relative to the other one. So that's what we saw earlier, where there was like a block sliding this way towards a projectile sliding this way. And one of the objects had to have negative velocity relative to the other one. In other words, it was subtracting its momentum away from the thing that had momentum in this direction. So because momentum is a vector, we sometimes see a negative sign dealing with that. But for the relative speed calculation, it's just, oh, how fast do objects see each other that are going in the same direction? This one's gaining on it at 0.2 meters per second. Even though it's going 0.65, every time it goes 0.65 meters in a second, this thing goes 0.45 meters in the same second. So it does catch up to it eventually because it's going faster, collides with it, and then it slows down, right? And this one kind of speeds up. Look at the relative speed of separation. It's also 0.2. So it's easier to calculate relative speeds than it is to calculate the 1/2 mv squared final, 1/2 mv squared final for this one, add those two. But if we did, we would show indeed that the initial kinetic energy equals the final kinetic energy. Because the relative speed of approach equals the relative speed of separation, that is a consequence of the fact that kinetic energy is conserved and the collision is elastic. So to answer, and this is a problem study we're using to kind of review as much physics as we can. So it's good to sort of make mistakes and give ourselves feedback and say, oh, okay, there's two ways I could answer this question here, explain how I would check. I could, one, calculate the final kinetic energy just like I calculated the initial kinetic energy, because I know everything about the particles, right? Their mass and velocities. And then they should be equal. The energies before and after should be equal for the kinetic energy if it's elastic. But it's oftentimes simpler to just compare the relative speed of approach and the relative speed of separation. So you want to be able to calculate relative speed. And that's where we need to be mindful of. Same direction, subtract speed to calculate relative speed. Opposite direction, add speed to calculate relative speed. Here, they were all in the same direction. Everything was moving to the right in this example. The last one here is very similar to other questions that we've seen, using Newton's third law to explain why during the collision, the change in momentum of X is equal and opposite to the change in momentum in Y. It has to do with force is the rate of change of momentum. Newton's third law says the forces are equal and opposite. You need to say something that they're going to be in contact for the same amount of time in order for the change in momentum to be the same, right? Like if Newton's third law says the forces are the same, and we're trying to explain why the change in momentum is the same, we need to also say that the time that they are colliding, the time that they are interacting, or the time of collision is the same for both objects X and Y. Kind of what a collision is, right? They collide, they touch, they move on. All right, so you can put that in your own words for 2 marks there.